All right, welcome to Module 4, Lesson 4.2, Equilibrium of a Rigid Body, Part 2. For the objective today, we're going to expand the concepts learned about the equilibrium of a 2D rigid body into the world of 3D. Basically, it's all the same. You just have to then expand it into that third dimension. You've got the tools that you need. To kind of summarize what we've gone through so far this term, though, we have 2D and 3D applications, and then in the world of 2D we have the 2D rigid particle. This is one tiny dot, and for that we have the sum of forces in the x and sum of forces in the y. Those are our two equations of equilibrium. We don't have any moment equations because it's a rigid particle and size is not significant. For a 2D rigid body, we have three equations of equilibrium. So this is not a particle, this is a full-size body. So now we have sum of forces in the x, sum of forces in the y, and the sum of moments about the z-axis out of the page, about any point or points on the plane. And then 3D, we had a 3D rigid particle, and it's similar to the 2D rigid particle, except for that now we've added sum of forces in the z. There's still no moment equations. Everything's still concurrent through that one rigid particle. And now we have 3D rigid body. We have actually up to 6 equations of equilibrium. We have sum of forces in the x, y, and z, and then potentially the sum of moments about x, about y, and about z. So this is all of the equations of statics right here. So now that you've gotten exposed to the 3D rigid body, this is the most complex that the free bodies will get in statics. Similar to 2D, we do have to at least recognize and deal with the constraints and statical determinacy possibilities for a rigid body. If you have too many unknown reactions for the equations of equilibrium, then you have a statically indeterminate structure. Well, for 2D, that was 3 equations, sum of forces in the x, sum of forces in the y, and sum of moments about z. But now we have up to 6 equations of equilibrium. So indeterminate is in the 7+ range of unknowns. A problem that is partially constrained or unstable is when there are too few reactions for the number of equations. So if we have a 3D rigid body and we have 6 equations, if we only have 5 unknowns, then we are potentially partially constrained or unstable. And then if you have just the right number of unknowns to the number of equations, then you are statically determinate, just like there was before. Keep in mind there's still the special case of instabilities of parallel or concurrent reactions. So the skateboard now, you could have that being in 3D. It'd be like instead of a skateboard as looking at it as a line on the page, think about it as the 3D with the 4 wheels like a skateboard has. So there would be 4 reactions there, right, all vertical. But we don't have since they're all parallel, that it can be unstable. I was talking about the skateboard in the ditch in the last set of slides. This could be like a bowl, like a hemispherical bowl. All the forces, you might have reaction forces all pointing towards this center, but if they all go through some concurrent point and an applied force is not through that concurrent point, then you will have an instability, even in an otherwise statically determinate structure. This applies just like it did in 2D. It's just a bit more complex is all. Same with reactions. So similar to 2D, there are rollers and pins and fixed supports. There's also, you start to see journal bearings and thrust bearings. They're very common in mechanical engineering concepts. A journal bearing allows an axis to spin inside of it. So that's like it's a bearing that's like along an axle, and the axle is spinning inside of it. What it's doing is it's keeping that axle from moving up and down or left and right. So it's got those 2 force reactions that are the ones that are mutually perpendicular to the long axis of the axle. And then there are 2 moment reactions. It's allowing the spinning of the axle, but it's not allowing the axle to bend about the other axis. So this has 2 reaction vectors. And then thrust bearings are kind of like the journal bearing above. Thrust bearings are kind of like the journal bearing above, except for that they don't allow the axle to move in and out of the bearing. So they actually have 3 force reactions, X, Y, and Z. They still just have the same two moment reactions, and they still allow that axle to spin about its long axis. So those are kind of special cases of the items above. I would recommend you look at your text to see how they draw these in 3D, because since it's in 3D, there's even more variability in how this is drawn in problems based on which textbook you're looking at. Again, similar to 2D, here are the steps. Draw the free body diagram. Identify any two force members. You still have two force members in 3D just like you have them in 2D. Draw your reaction vectors as you see them. Set up your scalar equations of equilibrium. You now have up to 6, right? X, Y, and Z forces and X, Y, and Z moments. And then solve that system. You might not have all of those equations because you might have a problem that doesn't have unknowns in all those, unknowns and forces applied in all the directions. So each problem is going to be there's a greater ability for all of the problems to be even more different in 3D than they were in 2D. And then remember always that if you have trouble visualizing the geometry, if you can't figure out, because you have these cables going off in all different directions, don't forget, you can do their position vectors and then do the magnitude of their position vector and then find the unit vector from that and multiply it by maybe their force as a value or their force as your unknown that you're solving for. Develop those Cartesian vector forms of all the forces and moments potentially, and then grab all of your I forces and put them in your X equation, and then get all of your J forces and put them in your Y equation, and your K forces and put them in your Z equation. Okay, and then just do realize for 2D and 3D, moment vectors don't plug into force equations. They go into moment equations. Now, force vectors can find their way into moment equations because, moment equations can be either due to true couple moments or forces times distances. So you can have force times distance. Every term in a moment equation should still have a force times a distance. Kip, feet, pound, feet, kip, inches, Newton, meters, kilonewton, millimeters, whatever it is. And then, solve the system as you would normally. That's it for 3D. Good luck.